Point 1 Glaciers, a part of two basic cycles. Explain the role of glaciers in the hydrologic and rock cycles and describe the different types of glaciers, their characteristics, and their present-day distribution. Glaciers are a part of two fundamental cycles in the Earth system, the hydrologic cycle and the rock cycle. The water of the hydrosphere is constantly cycled through the atmosphere, biosphere, and geosphere. Time and time again, water evaporates from the oceans into the atmosphere, precipitates on the land, and flows in rivers and underground back to the sea. However, when precipitation falls at high elevations or high latitudes, the water may not immediately make its way toward the sea. Instead, it may become part of a glacier. Although the ice will eventually melt, allowing the water to continue its path to the sea, water can be stored as glacial ice for many tens, hundreds, or even thousands of years. A glacier is a thick ice mass that forms over hundreds or thousands of years. It originates on land from the accumulation, compaction, and recrystallization of snow. A glacier appears to be motionless, but it is not. Glaciers move very slowly. Like running water, groundwater, wind, and waves, glaciers are dynamic erosional agents that accumulate, transport, and deposit sediment. As such, glaciers are among the agents that perform a basic function in the rock cycle. Although glaciers are found in many parts of the world today, most are located in remote areas, either near Earth's poles or in high mountains. Valley, alpine, glaciers. Literally thousands of relatively small glaciers exist in lofty mountain areas, where they usually follow valleys that were originally occupied by streams. Unlike the rivers that previously flowed in these valleys, glaciers advance slowly, perhaps only a few centimeters per day. Because of their setting, these moving ice masses are termed valley glaciers, or alpine glaciers, figure 18.1. Each glacier actually is a stream of ice, bounded by precipitous rock walls, that flows down valley from an accumulation center near its head. Like rivers, valley glaciers can be long or short, wide or narrow, single or with branching tributaries. Generally, alpine glaciers are longer than they are wide. Some extend for just a fraction of a kilometer, whereas others go on for many tens of kilometers. The west branch of the Hubbard Glacier, for example, runs through 112 kilometers, nearly 70 miles, of mountainous terrain in Alaska and the Yukon Territory. Figure 18.1 Valley Glacier. This tongue of ice, also called an alpine glacier, is still eroding the Alaskan landscape. Dark stripes of sediment within these glaciers are called medial moraines. This is Johns Hopkins Glacier in Alaska's Glacier Bay National Park. Photo by Michael Collier. Ice sheets. In contrast to valley glaciers, ice sheets exist on a much larger scale. The low total annual solar radiation reaching the poles makes these regions hospitable to great ice accumulations. Presently both of Earth's polar regions support ice sheets, Greenland in the northern hemisphere and Antarctica in the southern hemisphere, figure 18.2. Smart figure 18.2 Ice sheets. The only present-day ice sheets are those covering Greenland and Antarctica. Their combined areas represent almost 10% of Earth's land area. Video. Greenland ice sheet stratigraphy. Ice Age ice sheets.
For decades, scientists have been probing the Greenland ice sheet from the ground, air, and space. Now a new study uses those observations to see within the ice sheet, laying bare a tale more than 100,000 years in the making. When we look inside an ice sheet, we can see distinct layers formed by thousands of years of snowfall. As snow accumulates, these layers get progressively compacted into ice, which then flows under its own weight. To get a precise history of a particular spot on an ice sheet, scientists drill into it and recover ice cores, which provide a record of the ice's age and what the past climate was like. Seasonal variations, along with ash from volcanic eruptions, show up in the cores, allowing us to date the ice and correlate samples from different sites. To extend this age information across the ice sheet, the best tool that we have is ice-penetrating radar, mounted on aircraft flying low over the surface. Radar transmits electromagnetic pulses into the ice and records the reflected signals, allowing us to track the depth of the layers detected in the ice. Since 2009, NASA's Operation Icebridge has flown over Greenland more than 100 times with a wide variety of instruments, including radar, and produced vast quantities of data, adding to the work from many other missions. This has allowed researchers to generate a three-dimensional map depicting the age of the ice throughout the Greenland ice sheet. This 3D age map shows that three distinct periods of climate are evident within the ice sheet. the Holocene, shown here in green, the last ice age, shown in blue, and the Eemian, shown here in red. The top layers from the Holocene period formed during the last 11.7 thousand years and are fairly flat and uniform, though the thickness varies depending on how much snowfall occurred. Below this, deeper within the ice sheet, we see layers that formed during the last ice age. Layers from this period are darker and more complex, having been further squeezed and sometimes folded as they flowed over the rugged bedrock below. Deeper still are layers of ice left over from the warm period before the last ice age, more than 115,000 years ago. Eemian ice can reveal how the ice sheet responded to a period of warmth similar to the one we are experiencing today. Several ice cores have recovered Eemian ice, but it is difficult to interpret. This new map of the age of the ice sheet shows that there is more Eemian ice than expected in northern Greenland, where it may be easier for scientists to collect and analyze. This new analysis reveals a 3D map of the age of the Greenland ice sheet, from the oldest Eemian ice, to the layers deposited during the last ice age, to the ice that formed during the Holocene. The response of the ice sheet to past climate change led to its current age structure. Further study will help us better understand how the Greenland ice sheet will respond to today's changing climate.
Ice Age ice sheets. About 18,000 years ago, glacial ice covered not only Greenland and Antarctica but also large portions of North America, Europe, and Siberia. That period in Earth history is appropriately known as the last glacial maximum. The term implies that there were other glacial maximums, which is indeed the case. Throughout the Quaternary period, which began about 2.6 million years ago and extends to the present, ice sheets have formed, advanced over broad areas, and then melted away. These alternating glacial and interglacial periods have occurred over and over again. Greenland and Antarctica. Some people mistakenly think that the North Pole is covered by glacial ice, but this is not the case. The ice that covers the Arctic Ocean is sea ice, frozen seawater. Sea ice floats because ice is less dense than liquid water. Although sea ice never completely disappears from the Arctic, the area covered with sea ice expands and contracts with the seasons. The thickness of sea ice ranges from a few centimeters for new ice to 4 meters, 13 feet, for sea ice that has survived for years. By contrast, glaciers can be hundreds or thousands of meters thick. Figure 18.3 Ice shelves. An ice shelf forms when a glacier or an ice sheet flows into the adjacent ocean. Glaciers form on land, and in the northern hemisphere, Greenland supports an ice sheet. Greenland extends between about 60 and 80 degrees north latitude. This largest island on Earth is covered by an imposing ice sheet that occupies 1.7 million square kilometers, more than 660,000 square miles, or about 80% of the island. Averaging nearly 1,500 meters, 5,000 feet, thick, the ice extends 3,000 meters, 10,000 feet, above the island's bedrock floor in some places. In the southern hemisphere, practically all of Antarctica is covered by two huge ice sheets that extend over an area of more than 13.9 million square kilometers, 5.4 million square miles. Because of the proportions of these huge features, they are often called continental ice sheets. There is more about Antarctica and its ice sheets in Geographics 18.1. The combined areas of present-day continental ice sheets represent almost 10% of Earth's land area. These enormous masses flow out in all directions from one or more snow accumulation centers and completely obscure all but the highest areas of underlying terrain. Even sharp variations in the topography beneath a glacier usually appear as relatively subdued undulations on the surface of the ice. Such topographic differences, however, affect the behavior of the ice sheets, especially near their margins, by guiding flow in certain directions and creating zones of faster and slower movement. Ice shelves. Along portions of the Antarctic coast, glacial ice flows into the adjacent ocean, creating features called ice shelves. These large, relatively flat masses of glacial ice extend seaward from the coast but remain attached to the land along one or more sides. About 80% of the ice lies below the surface of the ocean, so in shallow water, the ice shelf touches bottom and is said to be grounded. In deeper water, the ice shelf floats, figure 18.3. There are ice shelves along more than half of the Antarctic coast, but there are relatively few in Greenland. These shelves are thickest on their landward sides and become thinner seaward. They are sustained by ice from the adjacent ice sheet, and they are also nourished by snowfall on their surfaces.